All right, in this video, we're going to be looking at 5.6 indeterminate forms and L'Hopital's rule. So we're going to recognize limits that produce indeterminate forms, and we're going to apply L'Hopital's rule to evaluate a limit. This is definitely a topic that's normally covered in Calculus 2, but I also covered it in the Calculus 1 topics last time. I don't think I have any new examples here, but some of the examples are going to make a lot more sense now that we've talked more about e to the x in Calculus 2. So let's go ahead and make a note here that when we use L'Hopital's rule, we must state the indeterminate form and state that we're using L'Hopital's rule. You don't just assume that the reader is going to understand why you're doing what you're doing unless you tell them what you're doing. So the first thing that we're going to try always all the time is direct substitution. If I try direct substitution on this problem, the limit as x approaches 0 of e to the 2x minus 1 is going to be e to the 2 times 0 is 0 minus 1 over e to the 0 minus 1 is going to be 1 minus 1 is 0 over 1 minus 1 is going to be 0, and that's an indeterminate form. I'm just going to, from now on, abbreviate indeterminate form as IF, and our indeterminate form is 0 over 0, which usually means that we need to factor. So I see a difference of squares in the top there. Limit as x approaches 0, and I'm going to factor e to the x plus 1 over e to the x minus 1 over e to the x minus 1. I'll factor that, and then this will be the same thing as the limit of x goes to 0 of e to the x plus 1 is going to be e to the 0 plus 1 is 1 plus 1 is 2. Actually did the algebra step up there. Let's go ahead and do it down here. All right, let's get that there. And note here, e to the 2x is equal to e to the x squared. And we have the formula a squared minus b squared is equal to a plus b times a minus b. That's how we're going to address that one. What happens when algebra can't help us, as in this example down here? And I'm going to try direct substitution again. This is e to the 0 minus 1 over 0. 1 minus 1 over 0 is 0 over 0, which is an indeterminate form of 0 over 0. Typically, that tells us to do algebra and to try and cancel out that common factor that's there, but that's not going to work this time. So L'Hopital's rule tells us that we're allowed to apply it only in cases where we get an indeterminate form of 0 over 0 or infinity over infinity. So we can try algebra. Let's try it. This is going to be idea number 1. So let's try what we did before. Let's not just tell you that it's not going to work, not show you that it's not going to work. And we get stuck. We don't know what to do. So we can't do anything. Here. So we might want to try alternate algebra idea of let's take the limit as x goes to 0 and let's split this up into two fractions like this. And when we evaluate that, now we're going to get something that looks more like infinity minus infinity, which is another indeterminate form. And it's even a worse indeterminate form. It got better, not worse, or it got worse, not better. Sorry. So we need something else. Algebra didn't help. So we need something else from calculus. So what we're going to do with calculus is we're going to inspect which of these functions grows faster. And we're going to have some general rules about if the function on top grows faster than the function on the bottom, it'll do one thing for sure. If the function on top grows slower than the function on the bottom, it'll definitely do something else. And if they grow at like basically the same rate, then the derivatives are going to help us figure out what the answer to this limit is using something called L'Hopital's rule. So if f and g are differentiable functions that are differentiable on the open interval a to b and containing some point c, where I'm trying to evaluate the limit there, except possibly at c itself, then we assume that g prime of x is not equal to 0 for all x's that are in a to b except possibly at c itself, because it's going to be okay for us to get 0 over 0. If the limit as x approaches c of f of x over g of x produces the indeterminate form 0 over 0 or plus or minus infinity over plus or minus infinity, since those could be turned into 0 over 0 quite easily with reciprocals, then limit as x approaches c of f of x over g of x equals the limit as x approaches c of f prime of x over g prime of x. If you're getting infinity over infinity, just take the reciprocal and look at what's going on with that. So these are the indeterminate forms that are good, provided the limit on the right exists or is infinite. This result also applies when the limit produces any one of these indeterminate forms, like I just said: infinity over infinity, negative infinity over infinity, infinity over negative infinity, or negative infinity over negative infinity, which I just shorthand as plus or minus infinity over plus or minus infinity, like that. But most of the time, textbooks are going to just call that indeterminate form infinity over infinity and expect you to know that the infinities can have either plus or minus signs to them. All right, so now let's go ahead and go back to our motivating example and see if we can't use this calculus technique to help us evaluate this limit. So keep the limit symbol there. And we've already tried our algebra. We've tried our direct substitution. We know that this goes to 0 over 0 from above. So I'm not going to do that again, but I am going to take the derivative of the top, which is going to be 2e to the 2x. I'm going to take the derivative of the bottom, Oh, and now I have my 0 over 0 1 away, and I get 2e to the 0 over 1 is 2 times 1 over 1 is 2 over 1 is 2. And so the answer to my limit here is 2. Now, let's look at limit as x goes to infinity of ln of x over x. I'm just going to show you these graphs. Ln of x is doing this, and ln and y equals x is doing this. And that, yes, they're both going to infinity, but look how much faster y equals x is going to infinity. So we cannot do direct substitution here. We can evaluate the end behavior and see that this is going to the indeterminate form of infinity over infinity. So let's go ahead and apply L'Hopital's rule. Limit as x goes to infinity of 1 over x over 1. It's going to be limit as x goes to infinity of 1 over x is equal to 0. And that makes sense to me because the faster growing function is in the denominator. And that jives with when I had rational functions before and the degree of the bottom was greater than the degree of the top. And the horizontal asymptote always went to y equals 0. When I'm talking about x going to infinity or x going to negative infinity, I should be talking about a horizontal asymptote or a oblique or slant asymptote of some kind. So this makes sense to me that the quote degree of the bottom is greater than quote the degree of the top there, even though they're not polynomials, and that this should go to a horizontal asymptote of y equals 0. So let's go ahead here and think about what happens if x goes to negative infinity, the left-hand behavior of y equals x squared is like that. Y equals e to the negative x is like this. So in both cases, we're going to infinity over infinity, which is an indeterminate form. So let's go ahead and let's apply L'Hopital's rule. This is the limit as x goes to negative infinity of 2x over negative e to the negative x. And now we've got a linear function like that. And we have a negative version of this. This is like so. This is negative e to the negative x. And this is y equals 2x. I go to negative infinity here. This is going to negative infinity over negative infinity, which is still an indeterminate form. So let's use L'Hopital's rule again. And that's going to be limit as x goes to negative infinity of 2 over e to the negative x. Well, that's going to be the same thing as limit as x goes to negative infinity of 2e to the x. So e to the x looks like this, and just doubling the y values. So that 2 is not going to affect the end behavior out here. E to the x as I go to negative infinity is going to tend towards 0. So this is 2 times the limit as x goes to negative infinity of e to the x is equal to 2 times 0 is 0. All right, now let's go ahead and this is theorem 5 from the Larson-Edwards textbook. It's from section 1.5. So theorem 5 from section 1.5 of our Larson-Edwards textbook. And it says that suppose f and g are functions such that limit as x approaches infinity of f of x is equal to limit as x approaches infinity of g of x is equal to infinity. And it actually states this a little differently. Let me read what it says here. So limits at infinity of powers and polynomials. So let n, let me just write this out here. So limits at infinity of powers and polynomials. It'll say the same thing, it just will look different. So let n be a positive integer and let p of x be a polynomial. P of x is equal to a sub n x sub n plus a sub n minus 1, x sub n minus 1 plus dot 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 plus a2x squared plus a1x plus a sub 0, like that, where an is not equal to 0. Then the limit as x goes to either plus or minus infinity of x sub n is equal to infinity when n is even. If the degree of the function is even, it's going to have the same n behavior and it's going to match the leading coefficient here on the polynomial. So that's 0.1 here, 0.2, limit as x goes to infinity of x sub n equals infinity, and limit as x goes to negative infinity of x sub n equals negative infinity when n is odd. Also applies to n equals 1, even if it doesn't look like a polynomial to you and it's linear. That's just a first degree polynomial. And third thing to know here, limit as x goes to plus or minus infinity of 1 over x to the n. Doesn't matter what the power is here. If the power is in the denominator, is going to be equal to limit as x goes to plus or minus infinity of x to the negative n is going to be equal to 0. So this is for n is even or odd. So those are the three things to get from here. So, and they're just reminding you of your rules from pre-calculus here. And we talked about how fast things grow, that if the degree of the top is greater than the degree of the bottom, that it's going to go to positive infinity. If the degree of the bottom is greater than the degree of the top, or the bottom grows faster, then it's going to go to 0. And if they grow at the same rate, they're going to approach some constant m. So we normally deal with those with polynomials like this to tell us what to do. But now we're applying that idea of how fast something grows to functions that are not polynomials and saying we're just extending this concept from all the way back in section 1.5 to things that are exponential, logarithmic, and so on. So exponential functions are going to be the fastest growing functions that we've learned about thus far. E to the x, about the only thing that's going to surpass that later on is if we get to something that's going to be x to the x and the base is growing as well as the exponent. More on that later. Factorials will also grow pretty fast. Ln functions are the slowest growing functions that we've learned thus far. So you can just think of power functions somewhere in between, but that the higher the degree, the faster that it grows. So a fourth degree polynomial grows faster than a third degree polynomial, faster than a second degree polynomial, and so on. So that all applies to how L'Hopital's rule works really anywhere, but definitely we can think that way about n behavior and which grows faster when we're going to positive or negative infinity. All right, so there are other indeterminate forms for us to consider. We need to consider 0 times infinity. Well, that's an easy, this is almost one of the basic ones. This almost belongs in the other area, because if I take the reciprocal of this part, it's going to turn into an infinity over infinity. Or if I take the reciprocal of this part here, it's going to turn into 0 over 0. That's usually a one-step thing. Figure out which one is easier, which piece is easier to take the reciprocal of, and I get 0 over 0 or infinity over infinity. So we'll do one of those. That's very simple. These things that have an infinity in the base or in the exponent, but they have an exponent with them, all of these are going to require some advanced calculus techniques to be able to evaluate those limits. And we're going to do some examples of those. We did some examples of those in the Calculus 1 videos. And I have a feeling that you're going to be more comfortable seeing them now in Calculus 2 when we go back and do them again. There's also another type of indeterminate form here that's going to be infinity minus infinity, and we'll talk about that one in a little bit as well. We really don't like this one. This one's nasty. So that's my least favorite. If you can get this infinity minus infinity to turn into like a 0 times infinity is usually where you can get it to turn into, and then get it to a 0 over 0 or infinity over infinity. That's really good. So let's start off with 0 times infinity here. Like if we would try our substitution here, and let's again look at what e to the negative x looks like, that it's tending towards 0, and the square root of x is tending towards positive infinity. This is our indeterminate form, and we say, well, let's go ahead and bring this e to the negative x across the fraction bar, and make this limit as x goes to infinity of e to the x down there and the square root of x up here. And now it's going to go to 0 over 0. And we say, yay, we can use L'Hopital's rule, or we can just apply our theorem from above. So now let's look at square root of x, and we look at e to the x here. And they're going to maybe cross each other a couple times, but as we go out to infinity, remember e to the x is the fastest growing function, so degree of the bottom is bigger than degree of the top. So by we know this answer should be 0 conceptually by our theorem that we just talked about, but let's apply L'Hopital's rule. So before I do that, let's write this as x to the 1/2 over e to the x, so it's easier to apply the power rule. Now let's use L'Hopital's rule. It's going to be the limit as x goes to infinity, 1/2 x to the negative 1/2 over e to the x. And so that's going to be limit as x goes to infinity of 1 over 2 x to the 1/2 e to the x, and all the x's get in the denominator down there, and definitely 1 over infinity conceptually is going to go to 0. I can't do direct substitution, but I can say if all those x's are in the denominator down there, and I split 1 up a bajillion million ways, each piece is going to 0. So we try rewriting the expression in a form that yields an indeterminate form where we can apply L'Hopital's rule, and don't forget to try our old methods that we have from calculus 1 and stuff like that. This is a definition that maybe you learned in calculus 1. I know that the answer to that is E. I'm going to prove it to you now with logarithmic differentiation. Some fun calculus techniques, but this is one of the definitions of E, and it is why when this expression or something very close to it shows up in the compound interest formula, and we let the number of payments go to infinity, because we're doing continuously compounding interest, it's why the letter E shows up in there. So let's go ahead and let's just say L for the limit is going to be equal to the limit as x goes to infinity of 1 plus 1 over x to the x. And then I'm going to take the ln of both sides. And ln is one of those fun things where if I take the ln of the limit, it's the limit of the ln of the function. So I'm just going to let that ln pass right through that limit symbol like that. And then I'm going to use my log properties here. Sorry, not limit on that side. ln of L is equal to limit as x goes to infinity of ln of x times 1 plus 1 over x, like so. And if we look at that right-hand side now, ln of x is going to infinity, and this is ln this. Sorry, this is x ln of this. Right, some crazy stuff there, sorry. So this is going towards infinity times ln of 1, which is 0. And so we say, okay, let's look at which piece is easier to take the reciprocal of. I definitely think that it's x that's easier to reciprocate. Like this. And now when I take the limit, this is going towards, I already know this part is going towards 0. This part is now also going towards 0 as I go to positive infinity out there. So this is an indeterminate form. So is this one. Now this indeterminate form lets me use L'Hopital's rule here. And I'm going to take the derivative of the top. So that's 1 plus this times the derivative of what's on the inside. And then the derivative of what's on the inside here. Like that. Let's go ahead and rewrite that. That times a negative 1 over x squared. I'm really not interested in simplifying everything because that part and that part are exactly the same and make a 1. So this is limit as x goes to infinity of 1 over 1 plus 1 over x, like that. So ln of L is equal to, and I can evaluate this directly now, 1 over 1 plus 0. So 1 over 1 is 1. That's not our final answer because we need to say that L, our limit, is equal to e to the 1 is e. So our limit as x goes to infinity, 1 plus 1 over x to the x is equal to e. Just like we said, it was going to be because that's one of our definitions of e that we're going to talk about in calculus. We'll learn another definition of e later on. So what about something that's in the form of 0 to the 0 power? Let's think about sine x to the x. And as I approach sine of x from the right here, I'm getting closer to 0 from the top. And we know that 0, y equals x, we're getting close to 0 from the top as well. So this is something that's approaching 0 from the right, something 0 from the right like that, but that's an indeterminate form. I'm not really sure what's going on here. So let's use my same idea of L equals this limit. Once I get to this point, this is going to be, so I'm coming at ln of 0 here. I'm tending towards negative infinity. So I'm coming from the right. So this is going to be 0 times a negative infinity right now. So let's bring this x down. So this is an indeterminate form right now, but not the one that I want. Okay. So that's going to approach, now if I look at 1 over x, I come at 0 from the right. So this is a negative infinity over a positive infinity. That's an indeterminate form that lets me use L'Hopital's rule. So let's go ahead and do that. Limit as x approaches 0 from the right. Ln is going to be 1 over that times the derivative of what's inside, like that. And this is -1 over x squared, like that. So this is equal to limit as x approaches 0 from the right of a x squared cosine x over a negative sine x. And that's still going to 0 over 0. So ln of L, this is still going to 0 over 0. So we're going to use L'Hopital's rule again. Let's go ahead and let's write this as simplify this a little bit for myself before I use L'Hopital's rule. So this is going to be limit as x goes to 0 from the right, x squared negative. I'm going to put that up there. Cosine over sine is cotangent, but I want to take that to the bottom. And so when now I evaluate that, we already know x squared as I come from the right is going to approach 0. Cotangent as I come from the right is going to approach, I'm sorry, not cotangent, tangent. As I come from the right is going to approach 0 as well. So that's why I went ahead to rewrite this as a tangent. So this is going to approach 0 over 0, which is an indeterminate form that lets me use L'Hopital's rule. And that's going to be equal to the limit as x approaches 0 from the right of a negative 2x over a secant squared x. And now I'm going to evaluate that to be 0 over 1 times 1 is 1 is 0. And that is just not what we would have expected from the original, but it's true. It is getting close to 0 for ln of L. So wait a second. Are we done? We are not done, because ln of L is equal to 0, which means L equals e to the 0 is equal to 1. So we may need to take a natural log of the limit if there's an exponent, just to be, and then be sure to undo it at the end. It's very important to make sure to not just solve for ln of L, to remember to go back and solve for L. So that means the limit as x approaches 0 from the right of this sine of x to the x, which was this 0 to the 0 here, is actually equal to 1. It's quite amazing stuff. All right, let's look at our least favorite indeterminate form here of infinity minus infinity. And there are some ways when you do these problems that you can just get stuck in loops, and it doesn't help you. That's why we don't like this. So many times our old calculus 1 techniques are actually better at helping us solve these problems than just straight up applying L'Hopital's rule, and I'll show you that. So let's go ahead and just try to do quote direct substitution. Look at the end behavior here, y equals x at the end here. is going to be infinity, and then the square root of x squared plus 1, square root of x squared plus 1 is kind of gross looking. I won't try and draw that, but that's also going to go to infinity. You can look at that in your calculator and prove that to yourself, but this is going to be infinity minus infinity for our indeterminate form. So let's go ahead and let's try and rationalize the numerator, just like we did with difference quotients sometimes. And we'll put this over 1, say this is x plus, like this. And we'll say that that's the limit as x goes to infinity. X times x is x squared minus, this is going to be x squared plus 1 over x plus root x squared plus 1. And that gives me the limit as x goes to infinity of x squared minus 1 over x plus root x squared plus 1 is going to be a, just put this here, a negative limit as x goes to infinity, 1 over x plus root x squared plus 1, like that. And that is going to go to infinity in the denominator, and I have 1 in the top. It wouldn't have mattered here if I left this here. That's a constant in the top. So that's going to go to 0 as the denominator goes to infinity there, and we're done. So were there other ways that we could have handled this? Absolutely. We could have, for instance, taken the limit as x goes to infinity, and we could have tried to divide by x that was going to be positive, which would have given me 1 minus the square root of x squared plus 1 over x squared here. It's 1 minus the limit x goes to infinity of 1 plus 1 over x squared. It's 1 minus the square root of 1. So 1 minus 1 is going to be 0. We can do that. That's our old technique, and we would have gotten the same answer. And I think that sometimes those old techniques are just as good or even better than our new techniques. So suggested procedure for indeterminate limits, given a limit expression, try to direct sub where applicable, but remember that you cannot plug in infinity. If you need to just analyze the end behavior. If it's indeterminate, verify and indicate it. If the limit expression is in an appropriate form of 0 over 0 or plus or minus infinity over plus or minus infinity, try applying L'Hopital's rule and indicate that you're doing so. To do so, take the derivative of the numerator and denominator separately. You'll very rarely be using the quotient rule if you have a quotient in the numerator or denominator. So don't get L'Hopital's rule mixed up with the quotient rule. After applying L'Hopital's rule, simplify algebraically and try direct substitution again. If you attain another appropriate indeterminate form, keep repeating. If the answer is constant or infinite, you're done. If you get stuck in this loop, though, and you keep getting back to the same place, try something from Calculus 1 to break the loop. If your limit is to infinity or negative infinity, analyze your function behavior and or apply algebra. Multiply or divide by 1 over x to the n, where n is the highest power for rational functions of polynomials, and proceed appropriately. This is our technique from way back, in the beginning of Calculus 1, because otherwise you're just going to be doing L'Hopital's rule so many times based off of the power of n. It's the highest power that you just want to get rid of all those x to the n's if you can. Using your calculus 1 techniques, you don't need to use L'Hopital's rule when you're dealing with rational functions like that. Or when you can help get rid of the polynomial part and just look at the other part and see what it's doing. If the indeterminate form is one in which L'Hopital's rule doesn't apply, such as 1 to the infinity, 0 to the infinity, 0 to the 0, so on, force it into one of those using the logarithmic differentiation method that we showed, and then remember to go back and undo that when you give your final answer for what the limit is equal. Don't just forget and say the ln of your dummy variable is equal to some number. Go back and say your limit is equal to e raised to that power of the answer that you got. All right, so that's it for this video, and we'll come back next time and talk about 5.8. See you for the next video.